All right, so there are some interesting conclusions and expressions that we can use when we have an elastic collision, but it requires a bit of algebra that isn't really fleshed out in your book. So I wanted to make this video to sort of help you see how we get at these results. And I didn't use the Whiteboard because it's so writing intensive that wouldn't have been that efficient. So when we talk about an elastic collision, what makes it elastic is the fact that kinetic energy is conserved. That's a special situation because in general, in a collision, we can't always say that kinetic energy is conserved. What we can always say is that momentum is conserved. It doesn't really matter what kind of collision it is, but momentum will always be conserved. But in an elastic collision, we get these two conditions to use, and so it allows us to, for one, it gives us a lot more algebra to work with, but it also allows us to solve for more unknowns. So the way we're going to set this up is we're going to assume that we have a one-dimensional collision, so we're going to let everything move along the x-axis. Before the collision, we have two objects, object A and object B, are both moving along with their initial velocities. And then after the collision, they're moving along with their velocities, which of course we expect to be different. Now, if we applied the conservation of momentum to this situation, what we would get is we would look at the initial momentum of A, which would be MAVA1x. So A1x is its initial velocity for object A. We'd have MB times VB1x. And so those are the two objects that are moving before the collision, and that's what their momentum is before. After the collision, we look at the picture on the right. We have MAVA2x because that's its velocity after, and we have MBVB2x. Okay, so that's the total momentum after. And that's similar. We use conservation of momentum in a lot of situations, but this is new because we also can use another equation because of the fact that kinetic energy is also conserved because it is an elastic collision. And so we look at the total kinetic energy before and after the collision. And they're equal to each other. And so these are our two equations that we can use to help solve, to find, the idea being that we assume that we know what the initial velocities are, but we're trying to find the final velocities. And you know if you have two unknowns, you're going to need two equations, so these are the two equations. As they are, it's not that much fun to use them algebraically because of the fact that the velocities are squared in the kinetic energy conservation equation. And so we like to manipulate these in order to make them a little easier to work with. And to make things even easier, we are going to assume that the object B is initially at rest. And this is just going to simplify things a lot and let us do the algebra with less difficulty. But then the idea is that we can sort of assume that we can let that initial velocity not be zero because we can say, well, we just stepped into the reference frame that was moving with the speed of object B initially, and that's why it was zero. And then we can kind of go back and say, well, if it's not zero, if we step out of that reference frame, this is what it'll look like. So that seems a little confusing, but hopefully it makes a little bit of sense. So what I'm going to do on the next page is I'm going to take these two conservation expressions, but I'm going to write them in their simplified form without that initial velocity of object B. So what it's going to look like is our conservation of momentum equation will now look like this. Because we don't have any initial velocity for B, and our kinetic energy conservation will look like this. Now, what we're going to do is we're going to rearrange both of these equations. I'm going to take this expression and I'm going to rearrange it by solving for mb vb 2x squared. So I'm just, basically I'm going to multiply the whole equation through by 2, and then I'm going to move this term over here. And so I have 1/2, oh sorry, ma va 1x squared minus va 2x squared. And if you remember your algebra, that's the difference of squares, so I can factor that out. Into that. Now we're going to work with the conservation of momentum. And again, we're going to solve for the term, the final momentum of object B. And I can write this like that. So I'm going to call this equation 1 and this equation 2. And you might notice that if I divide those equations, I'm going to get a lot of terms dropping out. So that's exactly what I'm going to do. So I'm going to put equation 1 over equation 2. And you see a lot of things cancel out. For one, the masses cancel out. And so we don't need to worry about the masses anymore. It's important, I think, to notice that we didn't have to restrict the masses to be the same in order to get rid of them as we move forward with more algebra. So I crossed a lot of things out, and what I'm left with is this expression. And I'm going to call that one star. Let's make it red. That one is star. And I'm going to put that into equation 2. So that's the next algebra that I'm going to do. So I'm going to be taking this expression. I'm going to use this to substitute in for the final velocity of object B, the final momentum. So I have mb times va1x plus va2x is equal to ma and then I am going to just do a little bit of algebra, because what I want to be able to do is to solve for the final velocity of object A. So so we've just done a series of algebra steps, and in the next slide I'm going to solve for VA2x. So let's do that. So what this is doing is this telling us that there's an expression for the final velocity of object 2 in terms of its initial velocity, and so that's really helpful. I'm going to take this one and I'm going to put it in the equation that I had marked star. I'm going to rewrite it since we don't see it on this page, just so we that was equation star, so we're just going to be substituting this in here. And this is going to be easier if I find a common denominator. Now, because of this, these two terms will cancel out, and this will simplify to twice the mass of A over MA plus MB times VA1x. So these are our two results. Basically, we have found, because the equation was deemed to be elastic, and remember, the initial velocity of object B was 0, we were able to find the final velocity of both objects. Now, this is kind of an interesting, to use this for different scenarios is kind of interesting. We can look at a scenario where the mass of A is a lot bigger than the mass of B. So we might imagine a scenario where A is coming at B with its initial velocity, and then here's B, trying to show that it's really small. And of course it's stationary, and so this is what things look like before. And so we're saying, well, what does things look like after? So if mass A is a lot bigger than mass B, when I look at my first equation, let's number them again. I'm going to restart, and this one is 1, and this one is 2. When I look at equation 1, I can basically neglect the mass of B compared to the mass of A, so I can almost treat mass of B as 0. And so what this reduces to, which equation 1 reduces to, is it's essentially equal to its initial velocity. So the idea is that object A continues, basically unfettered. It's not even really impacted by the fact that it hit the very small object. And the velocity of object B, again, if we sort of neglect the mass of B compared to the mass of A, and that would be in the denominator, this is going to be about twice the velocity of A. So it will acquire momentum because it got hit by this really giant object. Now, you might be concerned because at first glance, this really looks like a major violation of conservation of momentum. But what we're saying is because the mass, if I looked at the momentum of object B, I would have to multiply this velocity times its mass. And because the mass is so small, we would say that that momentum is really negligible. It's not that important, and so it's not as bad as it seems like it would be. Now, another case would be, of course, if A is a lot smaller than B, so it's really the reverse. So here's A. And so a lot of times they compare this, the big object is like a bowling ball and the small one is like a ping pong ball. And so in this scenario, again, if we neglect now mass A compared to mass B, then we would basically say that mass A is going to hit mass B and bounce off it and go in the opposite direction with virtually the same speed. So it just kind of goes in the negative direction. Where for object B, we don't really expect it to move too small, but we have this term here in front of the initial velocity of A, but this is so much smaller than 1. It's just like if it moves at all, it's going to just move at a fraction of the velocity of object A initially. And you can also look at what would happen if they were the same size, and so you can play around with these equations. It's very common to really look at this when you're talking about elastic collisions. Now, one last thing that actually is going to for us when we do problems is to get a conclusion about relative velocities in a scenario like we just described, where we have two objects that are making one-dimensional elastic collisions with each other. So if we go back to this equation that we had made star, this is what it was. Oops, this is 2x. And we can rewrite this we can just kind of put all the things that have, all the velocities that are after the collision on one side and all the velocities that are before the collision on the other one. Now, when we look at this, this is really talking about the relative velocity of B to A. So how fast is B going compared to A before, after the collision? And this one term is the negative of the relative velocity of B to A before the collision. Because remember, before the collision we said that B was going 0. Now it turns out that we can still use this general conclusion and allow the object B to also be moving before the collision. Our conclusion is that the relative velocity before and after the collision have the same magnitude but opposite signs. So we can rewrite this as VB2 minus VA2 is equal to minus VB1x minus VA1x. And so if you think all the way back to the very beginning of this video, one of the things I said is that we were looking at a scenario where we had two objects moving before the collision, and we wanted to find both of their final velocities. So we only knew the two initial velocities, but we didn't know the two final velocities. And because of that, we needed two equations, because you know from algebra, two unknowns, you need two equations. Initially, we had used conservation of momentum and conservation of kinetic energy, but the kinetic energy equation is tough to use because everything's squared, and it just becomes an algebra nightmare. So what this allows us to do is this becomes our second equation. So we can use, in the scenario where we have an elastic one-dimensional equation, we can use conservation of momentum and this equation that relates their relative velocities before and after. Makes things a lot easier. And we'll see some examples in class where we use that.